Welcome to this section on corrective measures. In this section, we shall look at vision transformers and how they applied in image captioning. The vision transformer was used in the CPTR paper entitled Full Transformer Network for Image Captioning by Wei Liu, Sihan Chen, Longteng Guo, Xinxin Zhu, and Jing Liu. In this paper, the authors consider the image captioning task from a new sequence-to-sequence prediction perspective and propose caption transformer as CPTR, which takes the sequentialized raw images as the input to the transformer, compared to the CNN transformer design paradigm. This model can model global context at every encoder layer from the beginning and is totally convolution-free. Extensive experiments demonstrate the effectiveness of the proposed model, and this model surpasses the conventional CNN transformer methods on the MS, that's Microsoft Cocoa dataset. Besides these great performances, they provide detailed visualizations of the self-attention between the patches in the encoder and the word-to-patches attention in the decoder, thanks to the full transformer architecture. So that said, instead of using a pre-trained CNN or faster RCNN model, this is a pre-trained object detection model to extract spatial features or bottom-up features like the previous methods. They choose to sequentialize the input image and treat image captioning as a sequence-to-sequence prediction task. Concretely, they divide the image, which is this for example, into a sequence of image patches to adapt to the input form of the transformer. Note that this image, which is of dimension, say by size, by height, by width, by channels, that's the number of channels, can be passed directly into this transformer encoder right here. So what is done is this is divided into patches as shown here, and then flattened and reshaped such that instead of having this, we'll now have a tensor of dimension by size, by it's not actually a sequence length, let's just say by n, then by p. So this is done such that we could have this tensor as output here, and this output now can be passed directly into the transformer's encoder. That said, to be more precise, what the authors did was that, supposing we have this input by size by 256 by 256 by 3, which is this image right here. Now, if we break this image up into several patches, now if each patch actually is of dimension 16 by 16 by 3, then we shall need 256 of such small patches to form this original image right here. In that case, our n is going to be equals 256, and then the patch number is this 16 right here. So coming back to the notations given in the paper, they say if they have this image x element of, that's x of dimension h by w by 3, specifying 3 color channels, then to get the number of patches, we'll simply take this h divided by the patch number times w divided by the patch number. In this example here, we have 256 divided by 16 times 256 divided by 16, which is 16 by 16, which is 256, which is logical. Now that we've understood how these patches are created from the original image, we now flatten them and then reshape. So in this example where we have 256 16 by 16 by 3 patches, let's just say 256 16 by 16 patches. So if we have an image like this, and then we have 256 16 by 16 patches. So we have 16 by 16, obviously by 3 because we have the channel dimension. Let's just keep that aside. So we're having 256 of these patches which form the image. Now what is done is that we take simply from the top right, that's from the top left right up to the bottom right, we simply align all these patches. So as you can see here, the top patches put out first, the next, and this finally. So basically what we do is we just align all these patches or flatten all these patches such that we now have 256 of such 16 by 16 patches. Now doing this will give us a tensor of dimension n by 16 by 16. That's not by 16 but n by 16 times 16 times 3. So once we do this, we have this new tensor. Obviously we have the batch dimension, and with this new tensor now we could pass it into an embedding layer, which then can be passed into an encoder layer, which consists of the self-attention and the feed-forward networks as we've seen already. Not forgetting the positional encoding, which we insert right here. So note that unlike previously in this model or in this architecture, there is no convolutional layers. We just simply create these patches, flatten and reshape them, then pass into the embedding layer, which then gets into our transformer right here. So this is our encoder, our transformer encoder. We get this output, we now pass into our transformer decoder. And also, since it's a fully transformer based model, we could visualize how each part of this image attends to each other, or each patch attends to each other in the encoder section, and also visualize how these patches attend to the words via this cross attention right here. We also have the decoder, which is exactly what we've seen before. We could now look at some of the results gotten using this model. We'll see that we have the CNN plus RNN based models, we have the CNN plus transformer based models, and then we have our fully transformer based model right here, which happens to achieve the best results with respect to the other models which have been developed previously. In this part, we have the data set and the implementation details. Now let's look at the ablation study. The authors conduct ablation studies from the following aspects. The first one, the different pre-trained models to initialize the transformer encoder. The second, the different resolutions of the input image. And then finally, the number of layers and feature dimension in the transformer decoder. All experiments are conducted on the K-party validation set and optimized by cross entropy only. Then the experimental results are shown in this table 3 right here, from which the authors draw the following conclusions. Firstly, pre-training vitals for CPTR model. That is, as you can see on this table, we obtain the best results when we pre-train the encoder on the ImageNet dataset. This means that we're gonna collect this image or the different images, then we pass this through the encoder, and then instead of taking this output and passing through the decoder layer, we instead reshape it and then pass through a classifier, which then will use this model to do object or image classification. Now, after pre-training this model on an image classification task, we then use this pre-trained weights as some sort of initialization for the encoder to now permit us train our model end to end. So compared to training from scratch using parameters of the visual transformer model pre-trained on ImageNet 21K, that's 21,000 data set to initialize a CPTR encoder, brings significant performance gains. Also, using the parameters of the VIT model fine-tuned on the ImageNet 2012 dataset to initialize the encoder further brings 1 point improvement on the CIDR score. Secondly, the CPTR is less sensitive to the decoder hyperparameter, including the number of layers and the feature dimension, among which 4 layers, 768 dimension shows the best performance. Then with respect to the input image resolution, the authors found that increasing it from 224 by 224 to 384 by 384 while maintaining the patch size equal 16 can bring huge performance gains. It is sensible that the fact that the length of the patch sequence increases from 196 to 576 due to the increase in input resolution, and that you can divide the image more specifically and provide more features to interact with each other via the encoder self-attention layer, is the reason why increasing the resolution of the input image from 224 by 224 to 384 by 384 comes with better results. Now, the way they obtain this 196 is simple. You take 224 divided by 16 times 224 divided by 16, you have 14 times 14, since 224 divided by 16 is 14. Recall our formula from what was given here. So basically, we obtained the 196 from this formula. Then when H and W equals 384, we have 384 divided by 16 times 384 divided by 16, which is 576. So we'll get back to this. We now look at the attention visualization. In this section, the authors take one example image to show the caption prediction or caption predicted by the CPTR model and visualize both the self-attention weights of the patch sequences in the encoder and the word to patches cross attention weights in the decoder. Recall that the way we're looking at this is attention of these patches with one another, and then attention of these patches with these words or captions. Then with regard to the encoder self-attention, the authors choose an image patch to visualize attention weights to all other patches. And as shown in figure 2, here's figure 2 right here. This figure 2. In the shallow layers, both the local and global contexts are exploited by the different attention heads thanks to the full transformer design, which cannot be fully fulfilled by the conventional CNN encoders. In the middle layer, model tends to pay attention to the primary object, that is the teddy bear in the image. The last layer fully utilizes global context and pays attention to all objects in the image, that is the teddy bear, the chair, and the laptop. So as you can see right here in the middle layer, we have this highest values on the teddy bear, as you can see right here. And then in this last layers, it not only pays attention to the teddy bear, but also to the chair and then the laptop right here. Then also visualizing the word to patches attention, that's attention between the image and then the words. We'll see how when generating the word teddy, for example, it pays much attention to the position where we have this teddy bear. Now for the bear, similar. Sitting now pays more attention to the chair. For the blue, pays more attention to the chair itself, attention to the chair, and then laptop, more attention to the laptop. So this kind of visualizations show exactly what's going on under the hood. Let's now see how to obtain those patches from an image. Suppose we have defined a patch size of 16. We have the image, we get the image that's loaded, then we convert it to an array. We add a dimension specifically on the 0 axis. We could print this out. We'll see we have this image of shape 1 by 224 by 224 by 3. Now we use TensorFlow's image.extract patches function to extract the patches from this image very easily. The way this works is by specifying this sizes list right here, where this is a patch size, so we could take this off and have a patch size. So by specifying this, we start with a 1, patch size, and 1. Then for the strides, now note that this size here is simply specifying obviously the size of the patches or of each patch, and then the strides here is a distance between the patch centers. That is, after breaking up the image into patches, the distance between the patch centers should be equals the patch size. So let's have this patch size and here patch size. And also note that the reason why we're focusing on this second and third dimension or first and second dimension, if we're starting from 0, so we're starting from 0, 1, 2, 3. The reason why we're starting from this dimension, we're focusing on this dimension and this other dimension, is because we are looking at this image to be 224 by 224. That is the height and the width. We are not focusing on the batch size or on the channel dimension. Then we have this rates, which we set to values of 1 and 1. Then the pattern is valid. So let's run this. We obtain the shape. Note that if we take 224 divided by 16, so it gives us 14, showing that from this original image, if we decide to form 16 by 16 patches, then we shall have 14 times 14 of them. Now that said, this represents the H divided by P we had in the paper, and the other 14 represents the W divided by P. So it means N equals 14 times 14, which is 196. And so we just simply reshape the patches. So we have patches equals TF the reshape of patches. Then we specify this batch size of 1. We could put a -1 here, or just put 196 since we know it's going to give us 196. We have 768. Now note that 768 is equals 16 times 3, since each of our patches 16 by 16, that's the patch size. So 16 times 16, and then obviously we have the channel dimension, so that's it. Here we have times. Okay, so we'll get back here and we'll run this again. You see now we have our batch dimension, we have the N, and then we have P square, that's 16 by 16 patch size square, times the channel dimension as given in the paper. So simply based on this, we could create a patch layer, which is this, and this patch layer takes in an image, goes through the same process we've just gone through, and then it returns the patches. Now forgetting that we need to specify this patch size here when initializing this patch layer. Let's start by showing the image. We haven't run this yet. Run this. We have our image. Now the dimension doesn't match because we have to take off the batch dimension, so run that, and there we go. Here's our image right here. We call on this patch layer by passing this image. Take this off. Okay, so once we have this set already, we can now print out the patch shape. So let's print this out. Print out the patch shape. Could have this. And then since we have 14 by 14 patches, we'll define this figure with figure size 14 by 14, so that we could put in each and every patch in every allocated position, and then we enumerate through all the patches. Now let's print out let's look at the patch size from this right here. We had a 196, 768. So it means that we have 196 different patches, and then each patch is of shape 16 by 16 by 3. That's why we have 768 right here. Now what we'll be doing is that for each patch we shall reshape this last dimension here such that we have 16 by 16 by 3. So let's get back to this. We see that when we reshape, we get the patch, we reshape it such that we have the patch size. We have the patch size, so 16 by 16 by 3, and this is gotten from the 768. So let's take this back, and that's it. Once we have the patch, we now show it basically, and then we take off the axis, run that, and there we go. We have the image, and then we have the different patches which make up this image. Let's now look at this slightly differently. We take, instead of the n root by n root, we have 1 by n root square. So that's it. Run again. Now it looks more like what gets into the model, as here we have each patch which is aligned in this one horizontal axis right here. Let's reduce the size of the image, the input image, that's 64, so that could be clearer. 64. Run this again. Okay, now this 64 by 64 is broken up into several patches. You see, we take this up to the end, and then we continue. So basically this is how it gets into the transformers encoder. Let's now define the embedding layer which comes just after this patching. So we have our embedding layer, self.embedding, which is going to be a dense layer where we have model size, number of output neurons. So here we also include the model size. That's it. And then after getting these patches right here, we do the patches equals embedding or self.embedding of the patches. Now note that the usual embedding layer we use in Keras takes in, say, a 2D input and outputs a 3D output. So let's suppose that the batch dimension is included. Now in this case where we have a 3D input, we shall have a 4D output, which is not suitable for the kind of problem we're solving. That's why we prefer to work with a dense layer for a replacement of our embedding layer. So that's fine. We now go ahead and insert the patch layer. We have also the encoder and the encoder layer which we've also inserted. So we have this encoder layer, encoder, and then the patch layer. From this, the full model gets described. There we go. We get the pre-outputs, the inputs. Let's put this before. We have the inputs and the pre-outputs. We rescale. We pass this rescaled input into the patch layer. We specify the patch size and the model size. After specifying this, we pass it and we get this output. This output now is passed into the encoder layer here, and then the output from this encoder is passed into the decoder together with the pre-outputs, and then we have our model which takes in the inputs, the pre-outputs, and has the output, the decoder output. So let's run this, and there we go. We have this model which is of about 3.5 million parameters. Also note that we could as well pre-train this encoder that's from the patch layer to the encoder layer. We could pre-train it on a classification task before fine-tuning it on this image captioning task. For this section, we shall just go ahead and train it from scratch. So there we go. We have this model. Let's increase the model size. Let's take, say, 256. So, and there we go. We have our model with model size 256. We now go ahead and train our model. So that's it. After training over several epochs, our model converges. We have this loss values, accuracy values. Then we can now go ahead to test our model. So yeah, we have the caption and we have the image which is passed into the caption function. So there we go. We have a man sitting in front of a chair in front of a unknown and unknown's machine. We can check out this other image. Take this off. A little boy in a brown shirt and a little girl in a flower dress are looking at the ground. So that's it. We've overfitted on our part of our validation set. We can now go ahead to train on the full data set while decreasing the loss slowly as it was given in the paper.